Hola y bienvenidos. Here's a quick one-liner. 3 men walked into a bar. The fourth one ducked. Maybe that was 2 lines. Oh well. In this video, we're going to learn the first of 2 powerful techniques to help us find antiderivatives. This one is called substitution. Let's take a look. The idea for the substitution method is to make a substitution so that the integral becomes simpler. And I think the best way to learn about the substitution method is to start with an example. So in example 1, we're asked to evaluate the integral, or the antiderivative of, x cubed plus x, all raised to the 5th, times the quantity 3x squared plus 1. Now that seems like a pretty complicated antiderivative to take. If we're trying to find a function whose derivative is that looks pretty complicated. What we're going to do, though, is make a substitution off to the right to help us simplify this integral. So we're going to let u, which is what we used for our chain rule, you might remember. That was like an inner function. We're going to let u equal x cubed plus x. That's a function that's inside this 5th power function. Now what we're going to do is take the derivative of u with respect to x. So we'll have 3x squared plus 1. Now for notational purposes, what I'm going to do is I'm going to write the dx over to the right side. So du, oops, let me highlight this so we can see what we're going to do with the substitution method. Du equals 3x squared plus 1 dx. And it turns out that this notation is going to be okay. We're going to justify it in just a little bit. So notice that the du is happening right here. This part right here is du. So taking the next step, putting it all together, we have the integral of, now instead of x cubed plus x, we can replace that with u because we let u equal x cubed plus x. So we have u to the 5th. And then instead of the part that's circled in red, the 3x squared plus 1 dx, we're going to write du. What we get is a much simpler integral. We can figure this out. We can figure out the integral of u to the 5th du. In other words, the antiderivative of u to the 5th du. We can do that by adding 1 to the exponent and then dividing by that exponent. Let's put our plus c before we forget to make it the most general antiderivative. But we can always double check and take our step back. If we turn around and take the derivative, then the 6 will multiply in front, we'll cancel off this 6, and then we'll subtract 1 from the exponent, and we get back to u to the 5th. Again, the derivative of a constant is 0. So derivative of this whole thing is u to the 5th. Now the only last step is to go back to x. We can replace u with x cubed plus x to the 6 over 6. And there we have the antiderivative of the function that we were starting out with. Now we can, again, double check everything by taking the derivative of this function that we got and double checking to make sure that that's going to be x cubed plus x to the 5th times 3x squared plus 1. And it is, because by the chain rule, we would have the 6 multiplying in front. Let me do that work off to the side, actually. So if we took the derivative, we would have the 6 would multiply in front, and we would it would cancel off the 6 on the bottom here, subtract 1 from the exponent, and we would get x cubed plus x to the 5th. But then by the chain rule, we would have to multiply by the derivative of the inside, right? Derivative of x cubed plus x, which is 3x squared plus 1. And that's exactly what we started out with. So this is checking out as the antiderivative. Now these steps do look really familiar. They seem kind of like the chain rule, but in reverse. They seem chain rule-ish. And that's where the substitution rule is coming from. It's coming from the chain rule of derivatives. It's like the analogy of the chain rule in derivatives is the substitution rule for antiderivatives. So here's a more formal statement of the substitution rule. We write if u is equal to g of x, so u is some function g of x that appears inside of the integral, appears inside the function we're finding the antiderivative of. If that's a differentiable function whose range is an interval I, and f is continuous on I, then the integral of little f of g of x times g prime of x dx is equal to the integral of f of u du. Remember, that's f of u, not fu. Now the thing is, this integral right here looks like the chain rule. This looks like if we took the derivative of a function, we would end up with something like this. We would have the derivative of the outer function, leaving the inside alone, and then times the derivative of the inner function. So actually, if we wanted to write this, we could write this as big F prime of g of x times g prime of x. Derivative of outer, if we create this other function that we're going to call big F, which is the antiderivative of little f, then this is exactly the result of the chain rule. It's the result of the derivative of big F of g of x. Because by the chain rule, you take derivative of the outer function times the derivative of the inner function. So what we're doing by this substitution is we're simplifying that part, that chain rule effect, and simplifying it to make us have a simpler integral that we can handle, hopefully. Now the proof of this substitution rule is like this. Suppose we have big F, such that big F is an antiderivative of little f, and u is some function that's inside, that's the inner function. Then on the left side of the substitution rule, we have left side, and our goal is to get to the right side, the integral of f of u du. So here are the steps we can take. We can realize that this right here is the result of the derivative of big F of g of x. So this is the result of the derivative of big F of g of x. Let's check that. If we took the derivative of big F of g of x, that would be derivative of outer, leaving the inside alone, times the derivative of the inner. And since we said that big F is an antiderivative of little f, then big F prime is little f. So these two inside parts of the integral are equal. We can take this step. But then here we have the integral of the derivative of a function. And in the last packet, we had mentioned that the integral and the derivative are undoing each other. They're opposite operations. One's doing a derivative, the other one's doing an antiderivative. So they're canceling each other off in effect. So what we get is big F of g of x plus c. So there's the plus c because of the general antiderivative. But then at this stage, we can replace g of x with u. And the entire expression now becomes a function of u rather than a function of x. So this step is the shift from x into u, from the old variable x into the new variable u. But then we can write big F of u plus c as the integral of the derivative of big F of u. So again, the integral and the derivative are undoing each other, and we can get back to big F of u. But we want to write it this way because then we have an integral form, which is our end goal. And big F prime here is little f. So we end up with the integral of little f of u du. So we got from the left side of the substitution rule to the right side of the substitution rule, which means that we can take this step. As long as we find this inner function, g of x, and replace it with a u, and we also have the derivative of that inner function with the dx, and replace that with a du, then we're okay. So a few notes. To use the substitution method, what you're looking for is a function whose derivative appears with the dx, whose derivative you can put right next to the dx, like sort of multiply to the dx, you can think. The function for u is usually going to be inside of another function. That's not always the case, but a lot of the times it is. And you'll want to make the substitution to have a new integral that's easier to integrate. That's the whole goal here, is to turn an integral that you can't do into an integral that hopefully you can do. And if it messes things up and makes things more complicated, well, maybe substitution isn't the right technique. And again, we'll look at a second technique in the next packet. Let's look at example 2. So we have the integral of secant cubed of 5x plus 1 times 5 dx. Now we could do this just by thinking about it, just by thinking about what such an antiderivative could look like. Let's try to use this new method. If we look for an inner function, what do you see here? If you said 5x plus 1 for the inner function, that would be correct. That would be a good inner function. Now, the derivative of this would be du dx equals 5. We can move the dx over to the right. So think about it as like multiplying the dx to the right. And we get du equals 5 dx, which we see right there. There's a 5 dx. There's a 5 dx. So we can rewrite this whole integral all in terms of u. We've substituted the x's out, and we're going to write this all in terms of u. This will become secant squared u du. Whoops. This is a much easier integral to handle, a much easier function to find the antiderivative of. Integral of secant squared u would be tangent u, and we'll put our plus c. Then we just have to make sure to go back from u, which was a temporary variable, back into x. This is using that relationship that was set up between u and x, between you and your x. On that note, we'll end this video and see you in the next one. Thanks for watching.